Hello. Hi everyone. Am I audible? Hello. Hope I am audible. Everyone. All right. So today we are going to discuss about floor planning in physical design. Okay. So this is the topic which we have chosen as the technical topic for discussion. So we are presenting it from Semicon Technolabs. So Semicon Technolabs is a 8 years old VLSI design and training company. Okay, and then I'm Casey, uh, taking the technical topic today for floor planning. So I have around 19 plus years of experience in VLSI and currently working as a senior director at Radiant Semiconductors, taking care of end-to-end product development. So today we'll focus on the floor planning part. But before we go to floor planning, so let's go through some of the basic things like ASIC design flow, right? So ASIC design flow, as we can see here, it starts all the way from system specification till chip finishing. So system specification, as we all know, so system specification is nothing but an idea where we have to plan as what kind of chip we want to make, whether it is medical application related or automobile related, or let's say consumer goods related, right? Now, system specification, once the idea is finalized, we move into architectural design where we map the specification into microarchitectural document, followed by RTL design and verification, which means from the microarchitectural document, so we'll be taking the digital portion, and in the digital portion, we'll be mapping it into RTL, either using Verilog or VHDL, and then this RTL has to be verified, which we call it as functional simulations. When we say RTL design and verification, the verification part is nothing but the functional simulations, right? Only if the functional simulations are passing, then we go for synthesis, right? I mean converting the RTL into gate level netlist. Okay, so once the netlist is available, right, then either we can go for DFT or we can jump in into physical design, right? So physical design, as we can see on the right side, I mean, lot of steps are involved in physical design, all the way from partitioning, floor planning, placement, CTS, routing, right? And today's topic is floor planning, where we will be covering part A of the floor planning. Okay, and next week again when we go live, I mean we'll be covering the remaining part B and the closure of floor plan. Okay, and sign off checks involves parasitic extraction, then physical verification, it can be DRC, LVS, antenna, then formal verification, which we also call it as LEC, static timing analysis. Again, in static timing analysis, we have gate level static timing analysis and transistor level static timing analysis. Okay, and power analysis as well. As you can see the eye diagram here, so power analysis, it can be power estimate related or it can be IR drop analysis, and also we have EM analysis. Okay, now once the physical design is done, and we'll be going deeper into floor plan topic today, then the next step is to send the GDS2 or OSS to foundry, where we will be doing the mask preparation followed by fabrication. So mask preparation means every layer is having a mask attribute. So those mask attributes are prepared by fabrication, and then finally packaging, because the die from the fabrication cannot be used directly for the product. So the die has to be covered with the package unit, and then the packaged unit has to be tested. Finally, the tested chip will be going to market. Okay. Now this is another cycle where we enter into full chip. Okay, so now initially chip design specification, right, as I was mentioning in the previous slide as well, the chip design specification will enter into architectural design, and from here the microarchitectural document will be taken into consideration, and then from the microarchitectural document again we have analog and digital in the microarchitectural document. Today's main agenda is towards digital portion. So digital portion of the microarchitectural document will be taken into behavioral modeling. So this behavioral modeling will be mapped into netlist. right? Logical implementation, that is nothing but netlist. And again, after netlist, we do the DFT insertion as well, right? Followed by physical design, and then finally sending the layout, right? Now, again, this has been elaborated a bit here, like chip specification, and then we enter into design entry, right? It can be RTL, again behavioral RTL or structural RTL, then synthesis followed by partitioning of the chip. If it is a very big chip, we partition it into multiple portions, and then finally add the DFT, that is nothing but controllability and observability, followed by floor planning, placement, CTS, routing, and finally verification and GDS2. Okay, so let's go to physical design in detail. Okay, so physical design, as we know, like partitioning followed by floor planning, power planning, placement, CTS, routing, and then followed by sign-off checks, right? I mean parasitic extraction, physical verification, formal verification, then STA, IR drop, and finally tape out. Tape out means like we are sending the final GDS2 to foundry. So the top steps from partitioning all the way till signal routing, this is called as PNR, and the below steps from signal routing to tape out, that is called as sign-off. Okay. Now, what is exactly the floor planning, right? So, in the design planning context, okay, floor planning is the process of sizing, shaping, and placing hierarchical cells and functional blocks in a manner that makes later physical design steps more effective. Okay, so overall, floor planning is an important stage in physical design because it directly impacts the performance, power consumption, and area utilization of the final chip. So if floor planning is not done properly, it will impact your PPA. We call it as PPA, power, performance, and area. A well-executed floor plan can significantly reduce design iterations and shorten time to market, okay, making it an essential step in the chip design process. So if floor planning is not done properly, we'll end up with a lot of iterations, to and fro iterations, okay. Time to market will be reduced. Now, floor planning in hierarchical flows provides a basis for estimating the time of the top level. A timing budget allocates the clock cycle time to each block according to the top level timing estimation, right? So when we are doing the partitioning at the top level, that time based on our partitioning only the budgeting will be assigned, timing budgeting will be assigned, right? Now, an effective floor plan helps ensure timing closure in many ways, okay, such as placing blocks to make critical paths short, preventing routing congestion that would lead to longer paths, and eliminating the need for over-the-top routing. We call this as feed-throughs, okay, for noise-sensitive blocks. The challenge is to create a floor plan with good area efficiency while leaving sufficient area for standard cell placement and signal and clock routing. Okay. In the floor plan, the size and shape of the chip or block are defined. Macros and IO cell placement is getting placed in such a way that effective routing space is available between the channel region and between the macro and IO regions. For standard cell placement, we keep the continuous core area for standard cell placement and optimization strategy from the target cell library. As you can see in the below image, this is mainly based on the design hierarchy, right? The macros and all are placed at the edges. Okay, in between we have standard cells, and you can see the hierarchy. Different colors are there: green, red, purple, blue, right? And these are the IO ports what we have for the block. If you see here, the IO ports are placed which are easy to connect to standard cells. The IO ports are not blocked by the macro placement. Okay, so these are some guidelines which we will go through in the coming slides. Okay. Now, what are the floor planning inputs and steps? Okay, the inputs to floor plan are gate level netlist, libraries, okay, logical and physical or reference libraries, timing constraints, techlef or .tf files. Okay, so these are the inputs. Okay, gate level netlist which we receive either from synthesis or from DFT, right? Then libraries, the libraries are coming from Foundry. We convert them into NDMs if it is like Synopsys Fusion Compiler or ICC2. If it is Cadence to Innovus tool, then we can directly use the .lib files and .lef files, right? That's where the logical and physical reference files come into picture. Okay. Then timing constraints, nothing but SDC. Then TecLef or .tf file. If it is Cadence Innovus, then we use TecLef, or if it is ICC2 or Fusion compiler, then we use .tf files. Okay. Now, what are the floor plan steps? Right. During the floor plan, the following steps are to be done. One, the initialization of a floor plan of appropriate dimension. First, we have to come up with the die area and die shape. That is the first step. Okay, we'll go through that in the coming slides as how to come up with the initial appropriate dimensions. Okay, then second step is, most of the times I have seen a slight confusion as should we place the IO pins or should we place the macros first. Usually it is better that we place the macros first based on the macro guidelines given by either the full chip team or given by the block owners, right? And then once the macros are placed, then we place the IO pins. Okay, macro placement considers the communication between them through fly lines. We have something called data flow fly lines. Using the data flow fly lines, we try to adjust the macro locations accordingly, because data flow fly lines will show the connectivity between macros. Okay, creation of power straps. So if you look at the diagram here, right, I mean we have rings. These are called the rings, external VSS and VDD. These are called the rings. These are called the pads. Okay, from the pads, the power and ground supply goes to the rings. And internally, we have straps followed by rails. Okay, so from pads, the power and ground supply goes to the rings. From rings, it goes to the straps. From straps, it goes to the rails. This is how the structure is defined. Okay, so ideally, if we have to say from pads, it goes to trunks. From trunks, it goes to rings. From rings, it goes to straps. From straps, it goes to rails. Okay, and from rails, the supply goes to standard cells. Okay, and whereas if it is macros, like for example memory macros or third-party macros, right, then the macros will be receiving power and ground supply directly from the straps, right, because they are bigger in size. Whereas the smaller cells like standard cells, they will be getting power and ground from the rails. So applying appropriate placement blockages near the macros, near the IO pins, densely packed cell names, right? We also need to make sure that the design is routable. That's where like we have to depend on the routing blockages and placement blockages to make sure that the congestion is in control. Placement of tap cells and boundary cells and end cap cells. Okay, so of late we are inserting tap cells, boundary cells, end cap cells, all these physical only cells in the floor plan stage itself without waiting till the placement stage. Okay, but however, in some methodologies we can even go for inserting these tap cells, boundary cells and end cap cells at the placement stage as well. It depends upon which methodology we are using, right? Now, if we see some of the floor plan guidelines, what are the guidelines which we have to keep in mind while doing the floor plan? Okay, the placement of macros is based on the fly lines, as I mentioned earlier, data flow fly lines. Okay, this is a snippet from ICC2, right? And we have an option here where directly we can see the data flow fly lines. Okay, it shows the connectivity between macro to macro, macro to standard cell. So we can minimize the interconnect length between IO pins and other cells. Now what will happen if we minimize the interconnect length, right? If we minimize the interconnect length, then what happens is automatically the net delay in the total path delay will come down. If the net delay in the total path delay comes down, automatically the path delay will come down, right? And similarly, because of very small net delay, the load on the cells also will come down. Thereby the cell delays also will come down. So overall, in summary, the total path delay will come down. Okay, so this is the advantage which will help in meeting the setup time, because data arrival time should be as less as possible in order to meet the setup time. Okay, and a good floor plan will become a platform for meeting the setup timing. If floor plan is not done properly, it will become difficult to meet the setup time, either with respect to memories or with respect to standard cells. Okay, now fly line analysis was done to locate the macro families and connections with standard cells and ports. Right, for a block we have IO ports, for chip we have IO pads. Okay, now fly line analysis helped to understand the importance of flipping and positioning the pin location of the macros to reduce the wire length connectivity. Okay. Now, if we have 4 floor plans being done by the engineer, right? How do we determine which floor plan is correct, right? The main thing which we look into is which floor plan has least wire length, because that will directly impact your timing. Okay, that is the major criteria what we look into while analyzing and finalizing which floor plan is correct. Okay. Now, what are the other guidelines? During the initial floor plan, right, placement, we shall perform flyline analysis followed by fan in fan out techniques during the next floor plan iterations. This will help us to converge design with less iterations. Okay. Place the macros around the boundary of the core, leaving some space between the macro to the core edge, so that during optimization, this space will be used for buffer or inverter insertion, and keeping large areas at the center of the core area for placement of standard cells during placement stage. Okay. So always need to make sure that the macros are placed at the edges. Okay, as we saw in the previous slide, right, the macros are placed in the edges. Okay, so that in the center we have space for the standard cells to be placed. This is always the best floor plan what we can do. Okay, if you place the macros at the middle, then the connections between the standard cells has to be detoured. So it is always good that you place all the bigger cells at the edges, leaving the middle space for smaller cells, that is standard cells, in order to avoid the detours. Okay, and to minimize the wire length. Now, place the macros around the boundary of the core, leaving some space between the macro to the core edge, so that during optimization, this space will be used for buffer or inverter insertion. Why do we need buffer or inverter insertion? The reason being, if we have to reduce the design rule violations, if we have to build the clock tree, right, then in both the cases, we need buffer and inverter insertion to be done, right? And keeping large areas at the center of the core area for placement of standard cells during the placement stage. Okay. Macros that are communicating with pins or ports of the core, place near to core boundary, right? Place the macros of the same hierarchy together, as we saw in the previous slide, right? I mean, all the macros, right, related to the same hierarchy, all the standard cells related to the same hierarchy, they should be placed close to each other, so that, right, I mean, the timing, closure of timing will be easy. The connectivity will be small, right? Now, keep a sufficient channel between the macros. What should be the channel generally we need to keep, right? Generally between RAM to RAM channel, right? We need to make sure that at least one tap cell is present, right? And then two end cap cells are present, and then at least one big size clock buffer and one big size clock inverter pair. If we place all these cells side by side, that is one tap cell plus two end cap cells plus one clock buffer, one big drive strength clock buffer, plus two inverters of big drive strength, clock inverters. If you place all these cells side by side, the summation of the width, right, that is what at least we need to make sure that that much of spacing has to be kept as a channel between macro to macro. And of course, you need to have one VDD stripe and VSS stripe going between the macros. Okay, so avoid notches while placing macros. This is very important, right? If anywhere notches are present, then we use hard blockage in that area. Placement hard blockage. Okay, avoid notches while placing macros. If anywhere notches are present, then use hard blockage in that area. Avoid crosstalk connection of macro placement. Okay, create a keep out margin around the four sides of macros, so no standard cells will not get placed near macro pins. This technique avoids congestion, right? By the way, congestion means the number of routing tracks are more compared to what can be supplied. Okay, the demand is more compared to supply. That is congestion. Congestion is purely related to routing. Okay, keep placement blockages at the corner of macros. For the pin side of macros, keep a larger separation, and for non-pin side, we can abut or adjoin the macros with their halo, so that area will be saved and the halo of two macros can be abutted, so that no standard cells are placed in between macros. Okay, these are some guidelines. Okay, between two macros, at least one pair of power stripes, as I was mentioning, right? I mean, one end cap, two end caps, one tap cell, one big size clock buffer, one big size clock inverter pair, right? We need to keep the minimum gap between RAM to RAM. And of course, we need to have at least one pair of power straps. power and ground should be present for a non-abutted floor plan. Okay, if you see here, these are the IO pads, right? And we have the power rings created, and these are the straps. The macros which are placed near to IO pads, the blocks with highest performance and highest power consumption. Okay, so whichever is having highest performance and highest power consumption, they need to be placed near to the IO pads. Okay, close to border power pads, IR drop, away from each other, EM. Okay, so IR drop, in order to minimize IR drop, we need to place these macros close to border power pads. But at the same time, you cannot keep both the macros at the same location. The reason being, it will lead to EM violations. That's the reason we need to keep them away from each other. Okay, multiple iterations happen to achieve an optimal floor plan. The chip designer takes care of the design parameters such as power, area, and performance during floor plan stage. Okay. Sanity checks. Okay, what are all the different sanity checks, right, which we have to do in order to start and go ahead with the floor plan? By performing sanity checks, we ensure that the input received from the library and synthesis teams is correct. Okay, non-performance of sanity checks leads to creating problems in the later stages of the design. There are 3 sanity checks, that is design or netlist checks, SDC checks, and library checks. Okay, design or netlist checks. Check if the current design is consistent or not. Checks like floating pins, multi-driven pins, undriven input ports, unloaded outputs, unconstrained pin mismatch, count between an instance and its reference, tri-state buffers and non-tri-state drivers, okay, and wire loops across hierarchies, right? So these are all things which needs to be checked, and for this we have a mega command called check design. So check design command in ICC2 checks for multi-driven nets, floating nets or pins, empty modules, pin mismatches, cells, or instances without IO pins or ports. Okay, so make sure that you apply this check design command, and all the above checks which has been mentioned, they are all coming out clean or at least understandable. Similarly, SDC or timing checks. Okay, if any unconstrained path exists in the design, then the PNR tool will not optimize that path. So these checks are used to report unconstrained paths. Okay, using check timing in ICC2, we can perform checks on whether the clock is reaching all the clock pins of the flip-flop. Check if multiple clocks are driving the same register. Okay, check if unconstrained endpoints, port missing input and output delay, that is set input delay and set output delay. Check port missing slew or load constraints. So entire timing related constraints we can check using the mega command check timing. But please make sure that you go with correct by construction approach, which means first you do the check design. Only if the check design is coming clean, then go for check timing. Without check design being clean, don't go for check timing, right? And finally, library checks. Nowadays, library checks are also incorporated into mega command check design. Okay, so what are library checks? What generally we check here? Okay, it validates the library, that is checks the consistency between logical and physical libraries. It checks the qualities of both libraries, logical and physical. Okay, check library command is used for library checks in ICC2. This command shows the name of the library types and their version, units of time, capacitance, leakage power, and current. It shows the number of cells missing and the number of metal or pins missing in the physical and logical library. Okay, so these are all the sanity checks before floor plan. Now, once the sanity checks are done, we are now aware of the floor plan guidelines. What is the importance of floor plan? How do we do the power plan, right? Now let's go into some area where like we have to estimate the die size. Okay, because optimal die size is the one where we have good floor plan. Okay, it should neither be more area, neither be less area. Optimal die size. Okay, because finally the design has to be routable and there should be very minimal or zero white space. Okay, once the netlist is read into database, we perform an initial floor plan to determine the dimensions of the chip as well as critical macro locations. Okay, there are some macros where like the location is very critical. If you don't place the macro in that orientation, in that particular location as defined by the full chip team, as defined by the neighboring block owner, then later on we cannot close on the timing part. Okay, that's why we call it as critical macro locations. The main goals of initial floor plan are to arrive at the optimum shape and size and to achieve the smallest die size to reduce the cost of the total chip and to be aware of signal integrity issues. The cost for the total chip depends mainly on the used space on silicon. Silicon is very expensive, and then wastage of die size, right? I mean, having white spaces in the die area, it will lead to wastage of silicon, right? In the future, it is not enough to pay more attention to the die size alone. The signal integrity issues like crosstalk, electromigration, hot electron, and wire self-heat become more important issues in deep submicron designs, and this influences the die size seriously. Okay, so first we need to come up with the die size estimation, and using this we need to calculate the die area. Okay, technology inputs, what all things we need for die size estimation. Okay, so technology inputs, gate density per square mm, right? Whenever we receive information from foundry or whenever we receive the PDK, right? So we have to make sure that we get this information, gate density per square mm. Okay, the number of horizontal layers, which we call it as H, the gate density per square mm we can call it as D, the number of vertical layers we can call it as V. So design inputs, what are design inputs we need for die size estimation? Okay, gate count, excluding memories, macros and subchip. What is the gate count? We can call it as G. Okay, now IO area in square mm, okay, we can call it as I. Memory plus macro plus subchip area in square mm, we call it as capital M. Target utilization in percentage, we call it as U%. Okay, additional gate count for CTS, timing closure, etc. in percentage, which we call it as T%. Additional gate count for ECO. ECO can be functional ECO, ECO can be STA ECOs, timing closure ECOs, right? In percentage E, right? Now, once we have all these different metrics available, then we go for die area calculation using these metrics. Die area in square mm, we can also do that in square micron meter. Okay, gate count plus additional gate count for CTS and ECO divided by gate density. Okay, plus IO area plus memory or macro area by target utilization die area. Okay, we have the formula here, G plus T plus E divided by D plus I plus M divided by U. Okay, the target utilization which you want to go, whether it is 60%, whether it is 50%, whether it is 70% or 50% or 40%, right? It all depends upon whether your design is a lower tech node design, whether your design is having low power UPF and CPF, whether your design is having abundant low power special cells. Okay, whether your design is power hungry, where like more number of layers has to be allocated for PG mesh, how many metal layers are available for the design. So many factors go into picture when we are finalizing the die size. Okay, now once we calculate the die area, right, again there are certain limitations that we cannot directly start applying the calculated die area. Okay, in core limited design, we have again two types, core limited and pad limited. If you see here, core limited means the number of IO pads are less, the die size is dominated or it is dictated by the core area, the cells present in the core area. Pad limited means the die size of the core area is very small, the standard cells and macros are very small, but then the entire die area is dictated by the IO pads. Because of IO pads, it becomes mandatory for us to go with the excess die area than what is actually required by the core. Okay, this we call it as pad limited. Okay, in core limited design, core is densely packaged, and in IO or pad limited design, IO or pads are densely packed, which limits the size of the chip. Okay, we cannot bring this down because there are so many IO pads. Okay, we cannot bring the size of the core area down, right, because it is IO or pad limited. Similarly here, even though the pads are less, we cannot reduce the die size because core area is more. Okay, there is a limitation here, there is a limitation here, core area limitation and IO pads limitation. Okay, now which limits the size of the chip. Pad limited, in this design there are so many pads that each pad is directly placed adjacent to the next pad. Although there is a small core area, it is not possible to get a smaller die size. The inputs and outputs from the chip are called pads. They are located at the outline of the die boundary. The portion of these cells may change when the floor plan is modified. Types of pads. Okay, there are again different types of IO pads in the full chip. Okay, input pads and output pads for the required input and output signals. Bidirectional pads. Okay, for bidirectional signals like buses. Power and ground pads to provide the required supply voltages. Pads establish contact between the chip and pins of the package. They protect the chip against electrostatic discharge. Okay, we call it as ESD. They work as amplifiers to boost the input and output signals. Core limited. The standard cells in the core need so much space that a smaller die size is not possible. Here the pads are not placed directly next to each other. Block limited. The design contains many macro blocks. It is not possible to place these macro blocks closer together to get a smaller die size. Okay. Package limited. If the package for the design is chosen before the die size is set up, the package limits the maximum die size because each package has a maximum space of the die. So these are all different limitations. Even though we come up with the die area calculation, right, we cannot exactly go with the die area calculation because we have other factors to take care. We need to understand if it is core limited, or is it block limited, or is it pad limited, or is it like package limited, right? Accordingly, we need to take a call on the final die size that can be used while doing the floor plan, right? Now, types of floor plan. There are again different types of floor plan. Okay, one is abutted, non-abutted, and mixed. Right, abutted floor plan, channelless placement of blocks. If you see here, there is no channel in between the blocks. Right, I mean block 1, block 2, block 3, block 4, block 5, block 6. There is no channel. Non-abutted, you can clearly see there is a channel, which means if I have to communicate the signals from block 1 to block 2, there is a room, right, in order to do the routing of these channels. Okay. Similarly, block 3 and block 4, if I have to communicate from block 3 IO pins to block 4 IO pins, there is a room where I can use this channel to do the routing of the signals, right? Whereas here we don't have the channel, which means the signals will be directly going from one block to another block, right? Directly they will get abutted. Okay. Now here it is not non-abutted, and we can use this channel either to place the glue logic or to give connections from one block to other block. Similarly, mixed. See here, from block 5 to block 6, there is no channel, whereas from block 5 to block 4, there is a channel. So it depends upon which way you want to go. Abutted, non-abutted, or mixed format in the floor plan. This also has to be finalized before we go for the full chip floor plan. Okay. Now, what are the floor plan control parameters? Right? There are some control parameters as well which we have to consider in mind. Right? First and the foremost is aspect ratio, width and height calculation, right? The aspect ratio is defined as the ratio of height to width, okay? Aspect ratio equal to height by width, which is nothing but number of horizontal resources by number of vertical resources, h by v, okay? Aspect ratio is equal to h by v, which means h is equal to width into aspect ratio. Die area is equal to width into height equal to width into aspect ratio. Okay, expressing h in terms of width function, right? So width square is equal to die area by aspect ratio, okay, which will give you the width. All right. Now aspect ratio is the main thing which we have to consider, right? This is one of the control parameters. It again depends upon how many routing resources are there in terms of horizontal or in terms of vertical. This will decide whether the block will be square shape, rectangle shape, rectilinear shape. Okay. Odd aspect ratio result is too much congestion and timing issues. It can, if it can be greater than 1, less than 1, or equal to 1, right? Which is square. Equal to 1 is always good, that is squarish is always good because you will have equal number of horizontal and vertical routing resources. If the aspect ratio is odd, it can be less than 1 or greater than 1. There are possibilities that it can lead to congestion and timing issues because either the width will be more compared to height or height will be more compared to width. Okay. Note, most of the algorithms work better when the floor plan is squarish, that is aspect ratio is equal to 1. If there are notches in the floor plan, the router needs to spend more effort to clean up the DRCs. Okay. Special care must be taken when there are notches to ensure that placement or routing density is not high on the edges. This is very important. Cell placement can be proper in squarish floor plans and hence timing can be met easily. If it is a timing critical block, try to get the aspect ratio equal to 1. Okay, try to get the die size equal to square shape. Okay. Now, if the aspect ratio is close to 1, then there is more availability of routing resources in both horizontal and vertical directions, right? The aspect ratio should consider the number of routing resources available. If there are more horizontal layers, then the rectangle should be long. See here, this is important. Based on your routing resources availability, whether it is in horizontal direction or in vertical direction, accordingly you need to choose the aspect ratio. The user has to choose the aspect ratio. If there are more horizontal layers, then the rectangle should be long, right? And the width should be small, and vice versa if there are more vertical layers in the design, right? So please bear this in mind so that you use the maximum advantage of the routing resources that are available. Okay. Now, another main important keyword in floor plan is core utilization. We keep using this word core utilization, right? Whenever we are doing projects, the first thing, the first question which we would ask is, what is the core utilization which you have used while doing the floor plan? Okay. So utilization will define the area occupied by standard cells, right? Macros and other cells. If core utilization is 0.6, that is 60%, that means 60% of the core area is used for placing the standard cells, macros and other cells, and the remaining 40% is used for routing purpose. Core. The core is defined as the inner block which contains the standard cells and macros. There is another outer block that covers the inner block. The IO pins are placed on the outer block. Concept of row. Okay, the standard cells in the design are placed in the standard cell rows. All the standard cell rows have equal height and spacing between them. The width of the standard cell rows can vary. The standard cells in the rows get the power and ground connection from VDD and VSS rails. We also call this as follow pins, okay, which are placed on either side of the cell rows. Sometimes technology allows the rows to be flipped or abutted so they can share the power and ground rails. Okay, we have something called row orientation key, right? Those who are using ICC2 or Fusion Compiler or Innovus, they can clearly see there is a triangle shape in the site rows, right? The triangle shape indicates row orientation key, which is nothing but the VSS follow pin. Okay. Now, standard cells utilization, right? Row utilization. How effectively are you using the standard cells row utilization, right? It is defined as the ratio of the area of standard cells to the area of the chip minus the area of macros and area of blockages, placement blockages, right? So area, standard cells by area of chip minus area of macro minus area of placement blockages. If you see here, low standard cell utilization, right? Here and there we have white spaces. We are not completely utilizing the standard cells area, row area. But here if you see high standard cells utilization, right? Now here on the left side, we are wasting the area, silicon area. Similarly, right, I mean the entire area, we are not effectively using it for the construction of the chip. On the right side, if you see, the standard cells are being used effectively, but then at the other side, there are possibilities of electromigration violations as well, EM violations, because of huge cell density. The cells are placed in cluster. Okay. Now, IOs in floor plan, right? I mean, what are the different IOs in floor plan which we have to deal with, right? The IO cells are the ones that interact in between the blocks outside of the chip and with the internal blocks of the chip, okay? In the floor plan, these IO cells are placed between the inner ring core and outer ring chip boundary. These IO cells are responsible for providing voltage to the cells in the core area. I mean, these IO cells can be again power and ground IO cells, signal IO cells, right? There are two types of IO cells. Chip IO. The chip contains IO pins. The chip consists of core, which contains all the standard cells and blocks. The chip IO placement consists of the placement of IO pins and the IO pads. The placement of these IO pads depends on the type of packaging. Block IO. The core contains several blocks. Each block contains the block IO pins which communicate with the outer blocks and cells in the chip. Pin placement is an important step in the floor plan which can be optimized based on pin placement requirements. The placement in macros utilizes M3 layers most of the time, so the macro needs to be placed logically. The logical way is to put the macros near the boundary. If there is no connectivity between the macro pins and the boundary, then move it to another location. So it all depends upon how good you are placing the chip IO pads, how good you are placing the block IO ports, right? So there is again a difference between the guidelines we need to follow for placing the chip IO pads and block IO ports. Okay. So these are all the main things which we planned for today's discussion, right? And then next week we'll be going through some of the other main topics of floor plan, as how to qualify whether the floor plan is proper to take it forward for placement, CTS, routing, right, and sign off steps. Okay, so we'll pause here for any questions which we can take for the rest of the time, right? If not, then we can wrap up and then we can catch up next week for part B, which will be the closure of floor plan presentation. So any questions, anybody? Anybody has any questions? Is it clear? All right. If no questions, then I think we can wrap up today's session and then we can catch up next week. Thank you. Thank you so much, team, for the time, and then have a nice day ahead. Thank you.